In the previous video, we saw that a function is a well-defined relationship between the elements of two sets. And if one focuses on the idea of a relationship, then the best two ways to represent a function are mapping diagrams and graphs. In a mapping diagram, the arrow linking the two elements is clear, and in a graph, the coordinates of a point indicate which element is in the domain and which element it is linked to in the range. So the idea is that both those methods of representation focus on the idea of the relationship between the element and its image. If we now focus on the well-defined aspect of the definition, where a function is a well-defined relationship, then our priority would be to find a rule that allows us to calculate the value of y given the value of x. Now, let's say that for a certain function, the rule is to multiply by 2 and then add 1. And let's assume that the elements of the domain are 1, 2, and 3. Then the elements in the range will be multiplying 1 by 2 and adding 1 will give me a 3. Multiplying 2 by 2 and adding 1 will give me a 5. Multiplying 3 by 2 and adding a 1 will give me a 7. And obviously the link is between each element and its image. The problem here is that you can see the relationship between 1 and 3, but you cannot see the rule. You cannot see the idea of multiplying by 2 and adding 1 unless you actually try to discover it from this diagram. And it's not a very practical way. So we have to find a different way to represent a function. And that is a function notation. The function notation, let's say we begin by the idea of the mapping. We need to give the certain function, the certain rule, a name. Let's call it f for function. You can use any other letter if you want. But f is such that x maps to, and the rule is we multiply by 2 and add 1. So we multiply the x by 2 and add 1. And this really mimics the mapping diagram. Because if x was 1, then this maps to 2 times 1 plus 1, which is 3. If x was 2, then this maps to 2 times 2 is 4 plus 1 is 5, which is exactly what we had in the mapping diagram here. Only in the case of this notation, we are using generalized arithmetic, that is algebra, and we have the value of x that stands for any number, any element in the domain. Even though this is function notation, it is mostly referred to as mapping notation. Because it still maintains the idea of a mapping, as can be seen here. Now, we can develop yet another function notation, which is the one that is most common, and that is f of x is equal to 2x plus 1. This says exactly the same, but it says that when x enters into the function f, it becomes equal to 2x plus 1. And in this case, we can say, okay, what is f of 1? That is when x is in the domain. This is 2 times 1 plus 1, which is 3. Note that there are no arrows now, only equal signs. And f of 2 equals 2 times 2 is 4 plus 1 is 5. So 2, which is inside the brackets, maps to 5. And this is what we call a function notation. And this is the most common notation that we need to get used to. Also, there is another way to represent functions, which is block diagrams. In a block diagram, you imagine that x is coming into an operation, and if we're multiplying by 2 and then adding 1, then x is coming in. This box says multiply by 2, and what goes out is obviously 2x, and then the next box is another operation, which is add 1. So what goes out is 2x plus 1. Now, in a block diagram, you're breaking down the processes that occur to the domain, the element in the domain. Again, if you think of, let's say, when x is 1, you multiply 1 by 2, you get a 2. You add 1 and you get a 3. So 1 goes in, 3 goes out. X equals 1, 2x plus 1 equals 3, and so on. So in a block diagram, we have something like an input, which is the x, a process, which is the set of rules, and an output, which is the 2x plus 1 in this case. And we can put things together now. Y, which is our range, is equal to f of x. And this reminds us of the idea that y is a function of x. Y depends on x. But the rule for f of x is 3, in this case 3x plus 2. It's a different rule. Now, 3x plus 2 in its entirety is the output, but x alone is the input. So x is the input, it's the domain, which is the x value, but our output, which is the entire f of x, is 3x plus 2, and that's our range, which is our y. Let's take examples. Let's say that we're considering f of x equals 3x plus 2. In this case, we're not specifying what the domain is. If we don't specify what values of x we're concerned with, then this implies that x is the set of real numbers. So x belongs to R. And we can draw a table of values. Let's say x is 1, 2, and 3. This would give us y as 5, 8, and 11. Now, note that I used y here. Keep in mind that it is also f of x. And this is, again, y, which is f of x. And you've seen that before. You've seen that when you drew straight lines in grade 8. So if we take those values and we plot them on a pair of Cartesian coordinates, we get this line. Note that the arrow here and the arrow here indicate that this line extends in both directions. And we can write here y equals 3x plus 2. That tells me what the equation of this line is, or I can say f of x equals 3x plus 2 if I want to. We'll get back to that. And if we take another example, let me call the function g in this case. G of x is equal to 2x minus 5. But I'm specifying that my domain must be between -1 and 5. So if I take values of x to calculate the corresponding values of g of x, I cannot go below -1 and I cannot go above 5. So let's say -1, 1, and 5, for example. When x is -1, this is -2 minus 5, that's -7. When x is 1, this is 2 minus 5, which is -3. And when x is 5, this is 10 minus 5, which is 5. And again, we can plot those points, and we end up with another straight line. Note that the ends are two circles that have been filled in, indicating that those are two values that are included. And here again, we can write our equation as y equals 2x minus 5. So you might ask, well, why do we need function notation? Why not use equation notation? After all, we've been used to that, and it worked very well. And it's a very good question. Consider that you have the two functions here. They're drawn together. And remember, this is y equals 2x minus 5. And this function is y equals 3x plus 2. Now, if I say the point where y equals 4, which point am I talking about? Am I talking about this point where y equals 4? Or am I talking about this point where also y equals 4? It's not clear. So if I give each function a different name and I stop using y and I use, we had this was f of x, and this was g of x. So when I say that when g of x is 4, then I know that I'm talking about this particular point. And when I say that when f of x is 4, then I'm talking about this one. So giving functions a name reduces ambiguity, especially when you're dealing with more than one function. But there's also another reason. Compare the following. Compare the statement when x equals 1, y equals 5, which is what you would expect from an equation, to a statement like f of 1 equals 5. Now, this statement is a lot more efficient. It includes your x value and it shows you your y value. Here you had to give them separately. So this is a very efficient notation. It tells you your x and your y in the same statement. One final word. If we have a function that passes through this particular point, let's say it's 1 and 2, we know that the coordinates of this point are 1, 2. That's how we represent them, as an ordered pair. But for the 1 alone, we call it the location of the point. And for the 2, we say it is the value of the function at x equals 1. And both of the 2 together, this ordered pair, is called the coordinates of this particular point. So remember, location is the x-axis. The value of the function is the y-coordinate. And both of them together are called the coordinates of the point. So let's summarize. Functions now may be represented in 2 more ways. Algebraically, which is the function notation and the mapping notation. Function notation is more common. And we can represent functions in block diagrams. In a function, you have to specify the domain. But if you don't, then it is assumed to be the set of real numbers. And finally, function notation is practical and avoids ambiguity.